the concept of lowering in vapor pressure. We have imagined a closed container in which pure solvent is present. When non-volatile solute is added to the pure solvent, the vapor pressure of the pure solvent in the solution is lowered. We have seen this. So consider that P10 is the vapor pressure of pure solvent. This is pure solvent, and for this pure solvent we have considered its vapor pressure is P10, and P1 is the vapor pressure of solution. We have considered P1 is equal to the vapor pressure of solution. So we already know that the vapor pressure of pure solvent is more, and vapor pressure of pure solvent is more, and after the addition of solute, the vapor pressure of solution, it becomes lower. So P1 is equal to vapor pressure of solution, and P10 is vapor pressure of pure solvent. So P1 vapor pressure of solution is less than P10, that means vapor pressure of solvent. Therefore, vapor pressure lowering is vapor pressure lowering. Lowering means first the vapor pressure of pure solvent is P10. Vapor pressure of solution is P1. Okay. So now there is a change. Initially the vapor pressure is greater, and after the addition of solute, vapor pressure of solution becomes less, P1. That means there is a change, and the change is shown by delta. Change in what? Vapor pressure. And therefore we have seen here vapor pressure lowering. Lowering means there is a reduction. The change is always such that the vapor pressure is always going to lower when non-volatile solute is added to pure volatile solvent, and therefore the change is given by change in vapor pressure lowering, that is delta P is equal to P10 minus P1. Okay, and this is one expression. What is this? Delta P, lowering in vapor pressure. Lowering in vapor pressure is equal to P10 minus P1. What is P10? Vapor pressure of pure solvent. Vapor pressure of pure solvent is always greater. And what is P1? Vapor pressure of solution. Vapor pressure of solution when non-volatile solute is added to the pure solvent, then always the vapor pressure of solution is less, and therefore the change will be when a non-volatile solute is added to the pure solvent, the change will be always delta P is equal to P10 minus P1. Okay. Now the vapor pressure lowering delta P is equal to P10 minus P1. This is one expression for you, and based on this expression we will study the Raoult's law related to this expression. You can say that means we have already studied the Raoult's law related to this. That means the for volatile component, but when we have studied both the components solute and solvent were volatile. Both the components were volatile. But here one component is volatile and one component is non-volatile. That means in a solution, a non-volatile solute is present and pure solvent is volatile. So here is also a binary solution, that one component is solute and one is solvent, but one component is volatile and one is non-volatile. So what is the Raoult's law for the solution of non-volatile solid states? One Raoult's law we have studied in the back video. Now we will study the Raoult's law for solution of non-volatile solutes, that is P1 is equal to P10 into X1. Okay. What is P1? Vapor pressure of solution. What is P10? Vapor pressure of pure solvent. And what is X1? It is the mole fraction of the solvent. One is for solvent, 2 is for solute. So X1 is the mole fraction of solvent. Now for binary solution means there is one solute and one solvent. So for a binary solution, X1, okay, you know that X1 plus X2 is equal to 1. That means the mole fraction of solvent and mole fraction of the solute. This sum is equal to 1. And therefore, see here, I have written X1 plus X2 is equal to 1. Therefore, X1 is equal to 1 minus X2. X1 is equal to 1 minus X2. So, you can substitute this value X1 in this expression. What is the expression? The expression is like this. This is the Raoult's law. That is P1 is equal to P01 into X1. Okay. And you have to substitute the value of X1 in this expression. That is 1 minus X2. So you will write here P1 is equal to, see here, P1 is equal to P10. P10. So in place of X1 you can write 1 minus X2. Okay. P1 is equal to P10 into, in the place of X1 you can write 1 minus X2. So the expression will become P1 is equal to P01 minus P01 into X2. See here, P1 is equal to P01 minus P01 into X2. Okay. Now see here, you can rearrange this equation as P1. If you transfer this on this side, then you can get the expression like this. That means P01 minus P1 is equal to P01 into X2. I have just rearranged this expression. If it comes on this side, it will become P1 minus P01 and it is minus. Then just like see here, P1, if it comes on this side, it will become P01 is equal to minus P01 into X2. Now, if you multiply whole this equation to this whole equation by minus sign, you will get minus P1 plus P10 is equal to, again it becomes minus minus plus P01 X2. Okay, P01 X2. So just by rearranging, I have written here P10 minus P1 is equal to P01 into X2. Okay. Just by rearranging, you can write this equation P01 minus P1 is equal to P01 into X2. Now this P10 minus P1 is nothing but delta P. See here, P01 minus P1 is nothing but delta P. So you can substitute the value here, and P01 minus P1 means delta P. So delta P is equal to P01 into X2. Delta P is equal to P01 minus delta P is equal to P01 minus P1. Delta P is equal to P01 minus P1. Therefore, delta P is equal to P01 into X2. Or you can write this equation as delta P upon. You can write this equation as delta P upon P01. Delta P upon P01 is equal to X2. So these whole expressions I have written at this space. So lastly, I will tell you that the Raoult's law for the solution of non-volatile solute is. Okay, I have given all these on the blackboard. So delta P is lowering of vapor pressure. P01 is the vapor pressure of pure solvent, and it depends upon X2. That's why lowering of vapor pressure is said to be the colligative properties. That means the expression delta P is equal to P01 into X2, or delta P upon P01 is equal to X2. So delta P is lowering of vapor pressure, P01 is the vapor pressure of solvent, P01 is the, both these values I have written here. So P01 is the vapor pressure of pure solvent, P1 is the vapor pressure of solution, and X2, and it depends upon X2. X2 means X2 mole fraction for the solvent and mole fraction for the solute. X1 is the mole fraction of solvent, X2 is the mole fraction of solute. In this expression, delta P is the lowering in vapor pressure, P01 is the vapor pressure of pure solvent, and now the expression becomes X2 is the mole fraction of solute. That means the lowering of vapor pressure depends on the value of mole fraction of solute, and thus lowering of vapor pressure is said to be the colligative property because it depends on the number of solute particles present in the solution. Okay, delta P is equal to P01 into X2. That means lowering of vapor pressure. Why it is a colligative property? Because it depends upon the, which property? Lowering in vapor pressure depends upon the number of solute particles present in the solution, and therefore it is a colligative property. Then next we have to see about the relative lowering of vapor pressure. That we will study in the next video.